All right. Well, welcome back. We're going to finish up with the transcendental functions with exponential logs. You don't see many of these, but just in case you need a little review and how to solve them, because they do come up. First thing you want to make sure you know are a quick review of the exponential log properties. These will come up more often than not in the future. All right, when we deal with integration and differentiation. All right, but make sure you know these properties. Just write them down or know how to get them on the internet or whatnot. Real quick review on how to use the log properties. Logs are exponents. Okay, they help break down exponents. I have several videos on how to do that, but I'm going to spend time on that. But just really quick, how do you do that? Well, when you have the product of powers, when you have two of the same base, you add exponents. In the same way, when you have a log, since log is the inverse of an exponential, that means if you have log base and you're multiplying, you actually can add the exponents together. When you have a quotient, log base b of m over n, log base b of m minus log base b of n, all right, because you're dividing, same thing when you divide two exponents, all right, you subtract, divide two logs, logs are exponents, subtract right there. If you don't know what I mean, I have several other videos online and you can find how these properties relate. Okay, well, really important, the power property. Whenever you power, you distribute. In the same way, if you have a log and you have power inside, it can distribute and put in the outside. Okay, using this property, this is where we find the change of base formula. Log base b of m is log base a of m over log base a of b. All right, so whatever the log is, m, b, usually we use a lot of times natural log of m over natural log of b, okay, or log base b and so on and so forth. So using these properties, if we want to condense this, so a quick review, all right. First off, whenever you have a log, I'm using natural log, it's a common one. What we do is, since we have a coefficient, this can be written as natural log of x to the third minus natural log of y. Because now, all right, we are subtracting two logs. Now this is a value and this is a value. And sometimes subtracting two of the same base, that's the same thing as dividing. So natural log of x to the third, we can write this over y. Okay, and that would be our expression, which can be written like that and so on and so forth. Okay, same thing here. If I have this, any coefficient next to log can become the exponent, so we can write it natural log. That's the first thing we do. X squared plus natural log of y minus 5 with a natural log of z to the fifth. I guess I can put negative z if I wanted to. All right, that'd be fine. During the positive. Next thing we have is natural log of x squared. Plus means we multiply the inside, so be multiplied by y. So adding means multiplying. Subtraction of the logs mean we're going to take both these, and this just goes to the denominator, so it can be z to the fifth. All right, that's what we have. Natural log of x squared times y over z to the fifth, and that's using the properties of logarithms. Okay. Another thing that you might want to do, just with the inverse properties, okay, is that, yes, logs are exponents. Now, you heard me say this, maybe I should start with this first. But if you know function composed of its inverse, when you have this, equals x. So if these are inverses, so f and g are inverses. Inverse expressions, all right, break each other down. We use inverse expressions all the time. We use the inverse, for example, if I have x, all right, minus y, or minus 2, all right, equals 3. Okay, how we solve this? We use the inverse property. So I get x by itself by adding 2. Negative 2 plus 2, this is the inverse. All right, and what happens is that these cancel out, turn to 0. That's what we call the additive inverse. All right, so anything plus its opposite will equal 0. That's an additive inverse. We also have dividing portions, where we have a, and we multiply by the reciprocal of a, that's going to equal 1. That's called a multiplicative inverse. They break things down. Well, with functions, essentially, if you compose two functions together, all right, they are inverse of each other, it will equal x. Now, why is this so important? Well, when we have functions that are inverses, all right, essentially, exponentials, if we have a to the x equals y, all right, and I want to find the inverse, okay, the inverse, we would switch x and y values, all right, that's how we find inverses. So we have a to the y equals x, so we switch x and y values, all right. And now we solve for, all right, we solve for a. Now, how do you solve for an exponent? Well, to solve for an exponent, you actually create a logarithm, because logs are exponents. So a log of base a of a to the y equals log base a of x. So if I log both sides of log base a, well, what happens is that since these are inverse of each other, they're composed of function log base a of a to the x, or a to the y. This would equal y log base a of x. All right, these cancel out, and I'm left with y. Kind of like when you subtract 2 minus 2 equals 0. Log base a of a to y cancel out, left with that. All right, so for example, when you have this, all right, where would be one like that? Okay, so well, let's just go through. In the same way, if I went the other way, all right, right here, we have 4 log base 4 of 9. Well, 4 and log base 4 are inverse of each other. So 4 to the x and log base 4 to the x are inverses of each other. All right, that means if I compose them inside of each other, so if I take this and plug it in for that value right there, okay, so 4 log base 4 of x, that would equal x. So I put that inside of the x value, that would be, all right, those would be inverse of each other, and would be equal x. And that's why right here, whenever you have properties of exponents, 4 log base 4, exponential, all right, this is exponent of 4, they cancel out, we're left with is 9. In the same way, we have log base 3, this very similar property here. 3 is the base of the log, 3 to this exponent, this is exponential, this is a log, they cancel each other out, we're left with is 4x, left with 4x, that's our answer, all right, because they're inverse of each other. 8 log base 8 of 5x minus 2. Well, 8 log base 8, exponential, they cancel each other out, we're left with 5x minus 2. There we go. Right here, log base 6 of, you have log base 6 of 6, 7x minus 9. Well, this actually could go to the exponent, but let's just leave it right here because this is a coefficient. Log base 6 of 6, these cancel out. We're left with 7x minus 9 because those cancel out. And now we can multiply this through, which would be 14, all right, x minus 18. And there we go. Right here, log base, or 10, or 11, log base 11, these will cancel out again. What's inside the log is 6x minus 3, because 3 is not part of the log, so it just comes along for the ride. And so we have that as our answer. Right here, log base 5 of 5 to 6, cancel each other out. We're left with 6. We have 4 thirds times 6 minus 7. Cancel, turn into 2. We have 8 minus 7, which equals 1. That would be our answer. Right here, E, natural log. Natural log of x is the same thing as log base E of x. E is Euler's number, all right, and that's what we have. So those are the same thing. And the same way as we see log with no base whatsoever, that is a base of 10. That's known as a common log. This is known as a natural log. Natural log. All right, this is known as the common log. I don't know why I was thinking of Star Trek whenever I hear common log. All right, so we have that right there. All right, that's what we have right there. So when we have this, all right, change the color. E, it's a natural log. They have the same base. They cancel out. We left with the inside. Inverse property is 21. Natural log of e to 2x minus 1. Once again, inverse property, cancel out. 2x minus 1. E to the natural log of 3x. All right, e, exponential, log, same base, cancel out. We are left with 3x minus 4. 4 is not part of that, and that would be our answer. That is how we're going to be using the inverse property a lot. A function composed of inverse, all right, equals x, and this property right here allows us to solve for exponential and logarithmic functions. All right, so with that knowledge, okay, let's do some trying to know with log and exponent. So how do we solve this? Well, whenever we give it a log function, just like all the other ones, we always start with direct substitution. Let's see what the values are. So if I have this, I'm just going to plug in this value. So we have e to the 0 power. Then we have sine of pi times 0. All right. And what do we got here? Well, e to the 0 power is 1. All right, e to the 0 power is 1 because anything a to the 0 power equals 1 always. That's one of the properties, so make sure you know that. Times sine of 0, sine of 0. Now, once again, sine, that 0 is over here. All right, 1, 0. All right, sine y. All right, what's the y value? 0, so we have 0. 0 times 1 is 0, and that would be our expression. So it is continuous. This function is continuous at 0. Now, same thing over here. If we plug a 1 in here, we have natural log of 1. All right, natural log of 1 over e to the first. E to the first. All right. Well, what would that equal? That would just be natural log of 1 over e. Now, we can simplify this. See how we have e right there? And we're going to do that. Natural log, we can do two different ways. We can change this, all right, using the properties of logs or the properties of exponents. This would be e to the negative first, right? 1 over e is e to the negative first. Well, natural log of e, if you recall, these are inverse of each other. Natural log is base e, and e to the negative first. These cancel out, and what we're left with is negative 1. Negative 1. We could also use the properties of logs if you want to use that. All right, right here, natural log of 1 whenever we're dividing. All right, dividing inside a log is the same thing as subtracting. Natural log of 1 minus natural log of e. Well, natural log of 1 is 0 minus natural log of e to the power of 1 is 1. 0 minus 1 is negative 1. All right, two different ways of getting the same answer. This one using properties, inverse properties and exponents. This one using properties of logs. Okay, so let's try some of this. First off, the limit of this right here, the limit as x approaches 0, okay? You have to know this property right here. The limit as x approaches 0, all right, of 1 plus x, 1 over x is equal to e, okay? When we plug this in here, this is what's known as also indeterminate form. There is a proof for this. I'm not going to go through the proof. This is like later on, all right, which would be easier to see. We can solve this, all right? E is a natural number. It keeps on going on forever and ever and ever. But this will, all right, eventually come to a value. All right, just to show you real quick, I'm going to pop up Desmos, okay? And we're going to create another value here, okay? I'm just going to write this in here. I'm going to go 1, all right, plus x. Then we're going to raise this to the 1 over x power, okay? And we're going to be approaching this value. I'm going to get rid of that. Now, as we get closer and closer, and I'm going to go right there. I'm going to create a table, all right? Values, oops, not for that one. I don't want that. I want this one. All right, here we go. Table of values for that one. All right, here we go, okay? Table of values, as we get closer and closer to 0. So if we put a negative 0.000, negative 0.0001, 2.72. That's what we get right there. Now, when you plug in 0 itself, we know is undefined. And as you plug in some different values, okay, close to 0, all right, very, very close to 0. So let's go to the other side, 0.0001. All right, you see that we are approaching the same value. All right, we're approaching the same value. All right, and so as we get closer to the left side, we can see that it's getting closer to this 2.72 number, and to the right side, get closer to that. And as you keep on adding a decimal, you get a closer and closer value, or all right, closer to 0, and they're approaching the same value from the right and left side. You can see that both graphically and numerically, right there, and that's what we have. So from here, that value that is approaching, we call E. All right, so that's one you want to know. All right, the limit as x approaches 0 of 1 plus x over 1 over x is equal to E. That's a basic common one. That's a oldie but a goodie. There are other ways of finding E, which we're going to talk about later on in this section, but for right now, know that one. Another limit, all right, so we have e to the 2x minus 1, and we have e to the x minus 1. And we have to take this going to 0. Now, plugging this in here, we have 4. Plug in 0, okay, I'm going to do direct substitution first. So we're going to solve this e. We have e to the 0 minus 1. We have e to the 0 minus 1. E to the 0 power is 1, so we have 4. 1 minus 1 over 1 minus 1. And you can see that we have 0 over 0. This is known as indeterminate form. We got removable discontinuity. Removable discontinuity. All right, discontinuity. The limit exists. but there's a hole there, so we have to figure it out. So this is indeterminate form. All right, so to solve a problem like so, all right, to solve this, what we're going to do is, you see e 2x, all right? Well, we can write this as an exponential, or sorry, quadratic form, okay? We're going to use properties of exponents. What we're going to do right here is we want to eliminate this denominator, so we're going to do a little algebra. This is the same thing as e to the x, that quantity, squared. And this is how we're going to rewrite it. E to the x minus 1. Now, the reason why we did this is e to the x squared, all right, e to the x squared, when you have that right there, okay, is very, very similar to if we had, like, if I had, like, a u equals e to the x. How would you solve that? Well, if I would rewrite it like so, we would have 4, it would be u squared minus 1 over, all right, u minus 1, right? Now from here, what we go through is that we would actually simplify this, and we have e squared minus 1, which you know we can write it as 4. This is the difference of squares, right? So we have u minus 1, and then be u, all right, plus 1. Well, what happens then, this and this cancel out, and we can see that, yeah, this is the same thing if I would have 4 times u minus plus 1, which is actually e to the x, so be e to the x plus 1. That's how we could simplify it. You could also write it as this, all right? Some students are really good at just saying, okay, this is squared. I'm just going to write it like so, e to the x plus 1, all right? E to the x minus 1, and you can see that these cancel out. In any case, where do you always end up? You end up right here. And guess what you have to do after that? Once you eliminate the whole, you then take the limit, all right, as x approaches 0 again. So what we get then, we plug in 0, we have 4, we have e to the 0 power plus 1. Well, that's going to be 4 times 1 plus 1, which actually equals 2, which will give us 8. And that's our limit. And that's our value. That's what we know. Same kind of deal down here. Okay? Very similar in doing our algebra. When we have this, e to the 3x minus 8, e to the 2x minus 4. All right? When we have this right here, we have natural log of 2. When we plug that in there, all right? E to the 3 natural log of 2. All right, minus 8. This is a little bit harder one. E2 natural log of 2. All right, minus 4. Right here, we cannot cancel these out right away. We have this coefficient. So what we have to do is we have to rewrite this using our properties of exponents, or properties of logs. Any coefficient is the same thing as the power, right? Same thing as the power. So we can actually write this as e the natural log of 2 cubed. All right, it's a cube right there. Cubed. All right, minus 8. And the same thing on the bottom, I can't just cancel these out. I have to get rid of the coefficient first. So we have e natural log of 2 squared. Put that on top. All right, some people say alley-oop, alley-oop. All right, put it up there. All right, for that property, and we have minus 4. Well, now that we got rid of that coefficient, we can now use the inverse properties. E to the natural log, this canceled out. We're left with 2 cubed minus 8. 2 cubed is obviously 8 in terms of 0. All right, this will then cancel out. We're left with squared, which is 4 minus 4. And what we realize is that, yes, we have 0 over 0, all right, indeterminate form. And so we got to do more work. All right, so the more work we got to do is we're going to take this, and yeah, we're going to rewrite it as e to the x, all right? That's going to be cubed minus 8 over e to the x squared, just like we did on top in the previous problem. Right here on the bottom, we can simplify this, and at the top, we can also simplify this as well, all right? And we're going to divide out a value into here, all right, that will be able to eliminate that. Okay, so what would be the value that we want to eliminate? Well, right here, all right, can we divide this value, okay, what would give us the natural log of 2? What would cancel that out? All right, so if we have this, this would actually simplify. We can have the top e to the x, all right, cubed minus 8. I'm going to factor the bottom. So we have e to the x minus 2. All right, and this is going to be e to the x plus 2. This is the difference of squares. Now the thing is, this right here is that I am going to then once again use some substitution because this makes it a little bit easier. If I said u equals e to the x, this makes my life a lot easier because now I can kind of see this a little bit better. All right, and seeing that, all right, when I have this value, okay, natural log of 2, that's the one right here. I have u cubed minus 8 over u minus 2, all right, u plus 2. Now, since this is 0 over 0, which one of these is going to be the factor that I want to factor out of here? U plus 2 is not going to factor out in that one. How do I know that? Because when I plug in, what will make this 0? What makes this undefined? What makes this 0? Is it u plus 2? No. It's a u minus 2 because, remember, we have natural log of 2, which is positive. Positive 2. So u minus, so 2 minus 2 is going to be that value. So what I want to do next is actually, I'm going to factor that out of there. Okay, I'm going to factor that out of there. I'm changing this into this area because e to the x makes it very complex. So I'm just going to divide u minus 2 out of u cubed minus 8. And I'm going to use long division to do that. All right, because that's what you probably know most. So squared, linear, minus 8. All right, so when we do that, I have u squared. All right, we can know the difference of q's as well, but if you forgot it, this is what you got to do. Minus 2u squared, opposite, turn to the 2u squared, bring down to 0. It's going to turn into plus 2u. We have 2u squared minus 4u, opposite, bring down to negative 8. All right, cancel out. We have 4u minus 8 plus 4. You probably see a pattern here. 1, 2, 4, 8. So what we have right here is going to be 4u minus 8, opposite, cancels out. We have 0. So there is our new expression. So what do we got here? When we rewrite this, okay, taking all this into account, I'm going to go back to purple. All right. So what do we have? When I cancel this, all right, this out of here, I'm left with is u squared plus 2u plus 4 over u plus 2. I canceled this out by dividing it out, getting a remainder of 0. And so now I'm going to re-plug in e to the x. I have e to the x squared plus 2 e to the x plus 4 all over e to the x plus 2. Let's now take the limit as x approaches natural log of 2. Re-plug it back in there. We have e to the natural log of 2 squared plus 2 times e to the natural log of 2 plus 4 all over e to the natural log of 2. Been another easier way I could have done it, but in any case, what happens, these cancel out. I'm left with 2. So now I got 2 squared. These cancel out. I'm left with plus 2 times 2 plus 4. Over the bottom, cancel out. I'm left with 2 plus 2. And going the other way because I'm running out of room. So I have 4 plus 4 plus 4, which is 12. All right, 12. All right, which equals 12 over 4, which gives us a limit of 3. All right, that's it. A lot of crazy algebra here. All right, a lot harder. All right, don't have all these all the time. This is a little bit easier one. All right, but give you some hard, easy, all right, not so hard problems. All right, and that, my friends, should allow you to complete this assignment. All right, this is the last part of this one, part 3. So what we just have gone through in this 3-part series is that you should know how to evaluate limits graphically, algebraically, numerically using a table. You should be able to determine if limits exist. You should be able to use the properties of limits to solve and evaluate trig limits. Use those properties of limits to solve any limit. All right, and evaluate exponential and logarithmic limits as well. Okay, so we'll answer some questions when we have class finally, but hopefully this serves you well. All right, so once again, please get this assignment done. All right, I will answer some questions on Friday. All right, but get that done for Friday. All right, thanks, and have a blessed rest of the week.